Dear friends, I want now to give you the opportunity to see the impact of changing the microstep resolution starting from a value of 256 microsteps per full step. This stepper motor makes 200 steps for a full 360 turn, which means 200 multiplied by 256 gives 51,200 microsteps for one 360 turn. You remember the last videos and the speeds we saw there. We will now go to an extreme so I can show you full steps by setting the velocity parameter, where on the second video we had 1 Hertz rotation speed by a velocity parameter of 490. We will change the velocity parameter now to 10 or 1/20 or just 5% of the total speed, and just play with the microstep resolution with this motor just to see the impact on rotation speed it has, changing two completely different parameters independently from each other and seeing the impact on speed. So now we will go and do a rotation left, and we'll set a next speed, set axis parameter, next speed value of 10. And now the motor starts. And if you watch the tape carefully, you see it rotating. Now I will go and change the parameter of the microsteps. As you remember, I told you we are starting with a microstep resolution of 250 microsteps per full step, with a velocity of 10 out of 2047. Which is effectively more like 4%. And now we will change from 256, which is the setting of 8, to the value 7, which represents 128 microsteps, and we'll double the speed. So now the speed has doubled compared to the one before, but it is still very low. Now we will go 4 times the speed by setting the microstep resolution to 6 or 64 microsteps per full step. It goes a bit faster again. Now we change it to 5. Please listen to the noise the stepper motor makes. Now we hear more electrical noise, but still no vibration. And it is moving faster. And now we go to 4, which is 16 microsteps or 320 microsteps for one full turn. 21. So it's kind of a half a hertz of speed. So when we go down now to 3 or 8 microsteps per step, we will already, at this velocity setting of 10, have a 1 hertz speed, while before, when we were working with 256 microsteps and the velocity of 490, we reach the same speed. So you see, having just a velocity of 10 compared to 490, by changing the microstep resolution to 8 microsteps per full step, we reach the same speed of 1 hertz, but doing more noise now. Now we will go and reduce it to 4 microsteps per full step. And we got now, and this is precisely 2 hertz of speed. We change to 2 microsteps per step, and this will mean we will have 8 hertz. This is now 8 hertz. And now we will go to 16 hertz or 16 turns per second by going on full steps. Now you get a very interesting effect. You see that the full step here gives a more silent, less vibrating operation mode. And this has to do with the relationship between the electrical parameters and the motor construction characteristics. Here you see that a full step rotation gives you 16 turns per second, much more silent. You see that now the power consumption is approximately half an amp and the voltage has dropped to 25.6 volts. Now we will go and increase the speed of the velocity of the motor. We had 10, sorry. Now, as this velocity is already pretty high, I will try to increase by 50%, which would be 6824 hertz, and it blocks. I think this is an interesting structure. You see how the motor is critical, and that often is the reason why people despair with the use of stepper motors. It is important to understand why it stops and when it stops. Here, the reason for the problem was, as I was running at full step, he was already pretty fast. When I increased the velocity from 10 to 15, I increased the speed by 50%. I should have increased it only by 1 to have a better result, but not being able to guarantee yet if it really will work, but we will look at it later. And you see the current consumption is down to 90 milliamps again.